Inverse circular functions are kind of a tangent from trig and kind of bringing back what we did in college algebra. When we studied college algebra, we learned that functions are defined to be, for a function f, every element in the domain corresponds to one and only one element in the range. One and only one, which means every input cannot repeat, has to have a unique input value for every unique output value. So if a point AB lies on the graph of f, then there is no other point that has A as an x coordinate. Otherwise, it is no longer a function, it is a relation. This is a vertical line test. No repeating your x's. All of these things from college algebra. However, the y's can repeat, so other points can have the same letter B as a y coordinate because the definition of a function allows output values to repeat, to be used more than once. Again, we have that vertical line test. This is all review for a second about what an inverse or what a function is. And then if we get a little bit further and talk about one-to-one function, this is when there are unique inputs for unique outputs. It is defined that a function, so already unique inputs, has unique output elements that is used only once. So it's no repeating x's, no repeating y's. If that's the case, it is called a one-to-one function. So just to kind of like throw it out there, since it is a function, point AB lies on the graph of f, then there is no other point that has A as an x coordinate. And if it is one-to-one, there is only one point that has B as a y coordinate. So a function can repeat the y's, no repeat x's. A one-to-one function, no repeat anything. In this case, we can use what's called a horizontal line test to check one-to-one. Vertical line test, since it's up and down hitting the x-axis, checks your x's to be unique. A horizontal line test checks the outputs to be unique. So putting it all together, a inverse function, which is what we learned about in college algebra for a little bit, is a one-to-one function defined as follows, which that's a whole lot of fancy notation to basically say all you do is you switch the x and the y. Do y'all remember doing that in college algebra?
No.
We switched the x's and y's and we resolved the equation for y. That's called f inverse. Remember doing this? Okay, so we have to go through all of this because to solve functions, you do inverse operations. AKA when you solve a linear equations and things are multiplied, you divide because it's its inverse operation. So we have to start developing these idea of inverse for trig. Just sticking on this example for a second, the last bullet point here says the graphs of f of x and f inverse are reflected over each other on the line, the diagonal, y equal to x. In college algebra, we learned that the steps to find f inverse are to switch the x and y, resolve the variable for y, and replace f inverse of x with that y variable. That's just good old-fashioned inverse functions. So if we apply this to the idea of our three basic trig functions, there's going to be a page for each of the three basic trig functions. You'll see almost immediately that there's some issues with this. By the way, I see some of them out. You will want your unit circle for this lesson and this unit. So go ahead and grab that as we're switching pages here. The inverse sine function. So, okay, inverse of multiplication is division. Inverse of addition is subtraction. Inverse of sine is inverse sine. Or arc sine. Correct. Before computers got math print, meaning before exponents looked like exponents, like it just looked like sine minus 1 if you typed this. So we developed this arc sine to indicate that it's sine inverse. However, this is more common now because computers are smarter. What's your question?
So will we need the arc sine?
Yes, they mean the same thing. They go back and forth. They mean exactly the same thing.
Could we use either?
You can use either or. I will naturally use this one because it's the one I prefer. They mean the same thing. You will see them both. They just mean the same thing. You can use whichever one you want. Mathematician's choice. However, these are the problems. Because the sine function is periodic, we know it looks like this. And that's a problem. Because does this currently, don't draw this, you'll be mad at yourself later. Does this currently pass the horizontal line test? No, so we have to do some work to restrict our function to where it does pass the horizontal line test. So if I take this function and I actually erase until I get from here to like here. Let me color this in a different color. If I look at this little section right here, if I only use like a horizontal line that's that long, Does that part pass the horizontal line test?
Yep.
Yeah, so we're saying what we're going to basically do is we're going to chop this graph off here and chop the graph off there. We are restricting the domain only between negative pi over 2 and pi over 2. We are restricting it only on your unit circle to quadrants 1 and 4, which would be negative pi over 2, and pi over 2. If we're finding sine inverse of some value, that means we're looking for the angle that would give me that value since we switched the x's and y's. Let's talk a little bit more about where we're looking for this. I have a bunch of representations of what sine inverse looks like. Since we're switching the x's and y's, if the sine function has a domain of all real numbers and a range of -1 to 1, that means we're just going to switch this over here, and sine inverse has a range from -1 to 1, and its domain we had to restrict, so we are only having a range of negative pi over 2 to pi over 2. And again, I think this image with the circle that's highlighted is probably the most important thing on here. Everybody take their unit circle right now, and I want you to fold it to where only quadrant 1 and quadrant 4 are showing. So like fold it in half. When you're doing inverse sine, the only answers you can use are on these two quadrants. So you can like basically forget about quadrant 2 and quadrant 3. Your only answers are going to be there. And here's the picture for it. Okay, so let's see what this might look like. If I ask you, keep looking at your unit circle, to find the value of y, if y is equal to the arc sine of 1/2. Look on that side of the circle. Can you find where sine, the second coordinate, would be 1/2? Yeah, what is the angle there? So y is equal to pi over 6. We're reading the unit circle backwards, inversely, if you will. Normally, you plug in an angle, you get out a measure, you plug in an angle, you get out a ratio. This time we're plugging in a ratio, getting out an angle. So let's look again. On that same side of your unit circle, can you find somewhere where sine would be equal to -1? Mm-hmm. Pi over 2, or it's negative though? Okay, great. I'm so glad you said 3 pi over 2. I'm going to draw you a picture for a second. I like that you said that because this angle, yes, is 3 pi over 2. And so to get there, I'd have to do this. Do you agree?
Yeah.
Are you allowed to go in quadrants 2 and 3 anymore? So is there another way I could get to this same spot right here without going around the whole circle? The other way. And if I'm going this way, is it a positive or a negative angle?
Negative.
How far did you go though? Negative pi over 2. So it's like you went to the 90 degrees except you went the opposite direction. That means this is negative pi over 2. Does that make sense? So you're not allowed to go in those other quadrants anymore for real, which means if you're trying to get down here to quadrant 4, you're just going to have to go negatively. Let's try it one more time. Y equal to sine inverse of -2. What is y? So is there a place on your unit circle where sine is equal to -2? No. So how do we answer this?
Great question.
No solution. It is impossible for sine inverse of -2 to be plugged in. There is nowhere that sine is equal to -2. The maximum and minimum value of sine is -1 and 1.
Wait, is this it? Like for that?
Yeah. Like these are basically like math facts. We're learning to read our unit circle inversely. Genesis does not trust me that that's all that it is. That's what that face says right there.
Wait, hold on. You said pi, I'm just trying to like get the best
Yeah.
understanding.
Yeah.
When you like negative pi over 2, like y'all just took away the 3?
So what we did basically is if you want an angle that's down there.
Because I know you can't go over it like 1 and oh wait, okay, I kind of get it.
Okay, so just as a little bonus, fold your unit circle back to where we're looking at inverse sine.
Yeah.
And if I asked you for the inverse sine of negative square root 2 over 2, where is negative square root of 2 over 2?
7 pi over 4.
Okay, 7 pi over 4. What color is that? Because all of ours are color coded.
Oh, that's
Pink, right? So it's pi over 4, but it's the one down. So what is the answer? Negative pi over 4. This is why we color-coded this so crazy. All of those angles go together. We'll keep practicing.
There's a method to the madness.
There's a method to my madness, absolutely. Let's see cosine. So we've done sine. Let's look at cosine. We can write it as inverse cosine or arc cosine. Again, there's going to have to be restrictions because right now, does cosine pass the horizontal line test?
No.
No, so we have to chop this graph off to where it does actually pass the horizontal line test. And where we're going to do that is like from here to here.
Yay.
That is from 0 to pi. It's a little bit bolded. It's not very sturdy, but that is going to be the only sections that we're allowed to use for cosine. Notice it is different than sine.
Mm-hmm.
On your unit circle, which two quadrants represent 0 to pi? No. 0
and pi?
to pi. How would you fold your unit circle?
Oh, it's the two top ones.
It's the two top ones. So now our function, which has a different domain and range, will now only take over the top graph, the top portion. Right? So again, if we're writing this down, the domain and the range switch for inverse, which means we should not ask a question that's beyond -1 and 1 because it's impossible, which we just saw on the other page. And we know that we had to restrict that domain between 0 and pi, which is why we are only in those top two quadrants. I find these images to be the most helpful. So if you're looking at your unit circle, let's do some values. Oh, sorry, what's up? Like which quadrants to use?
Yeah.
You have to start to know them. They never change. So inverse sine is always the number 1 and number 4.
So can I like only the domain, like say we're only using 5 and 0 and 5. Will it always coincide?
If it does something outside of it, it's an impossible question.
Wait, so is sine and tangent just this half and then cosine? Just saying that was
Wait.
making it worse.
Wait, can we write down?
You could do whatever you want on your unit circle.
Okay.
Those are your unit circles. But help me out here. If I'm finding the arc cosine of 1/2, in the top two quadrants, where is the first coordinate 1/2?
33
Pi over 3. So the arc cosine of 1/2 is pi over 3. The output is an angle when the input is a value for inverse sine, cosine, and tangent. How about the inverse cosine of -1? Yes,
Here's pi.
it's pi. How about the inverse cosine of -√2/2?
That's 3 pi over 4.
Yeah, with cosine, you don't have to do any of the negative stuff. You can just straight up read the unit circle. We'll pause here before lunch because the bell's about to ring, and we'll go over the last few things. The last function we have up here is the inverse tangent function. We're going to do all the similar things that we did for the other ones. Notice inverse tangent can be written tangent with a -1, inverse tangent, or arctangent. Again, because it's periodic, we have to restrict its domain. So right now, does tangent pass the horizontal line test? What?
No.
It does not, unless we take it and we do this. How about now? Does it now pass?
Yeah.
Great, so that means we're restricting this domain between -pi over 2 and pi over 2. One question.
Yeah.
When we did this for sine, these were brackets. Why are they now parentheses?
Because it's tangent.
Okay, tell me more.
Because of the asymptote.
Because of the asymptotes. We don't actually ever reach pi over 2 and -pi over 2 because of those vertical asymptotes, so we use the parentheses. But same thing like on the other side, our tangent, the range is going to switch over here, which means our domain is from -infinity to infinity. But, sorry, the range becomes the domain. Sorry.
Okay.
And the outputs, or the range, are what we have restricted to -pi over 2 and pi over 2. Exclusive. Which means, just like sine, we're going to be looking at quadrant 1 and quadrant 4. However, you can't go all the way around to quadrant 4. It's going to be the one where we do the negative thing.
Okay.
Are you ready to try?
No.
We're doing it anyways. What is the arctangent of 0?
0?
Where is tangent equal to 0?
No. There's 2 pi.
Wait, is it just 0? Wait, hold on.
Yes. So you're looking for where it would be 0 over 1.
0 over 1?
Zero.
So at angle 0. So arctangent of 0 is 0 because the tangent of angle 0 is 0.
Yay.
How about the arctangent or inverse tangent of 1?
Pi over 4.
Pi over 4, because the pink angle pi over 4 in quadrant 1 is square root 2 over square root of 2 over 2 or square root 2 over 2, which is 1. Also, if you flip it over, we do have those tangent angles on the back. What about the inverse tangent of negative square root 3 over 3?
Negative pi over 6.
So here's what you do. Look for just regular square root 3 over 3. What normally gives me square root 3 over 3?
Pi over 6.
Pi over 6. However, we want it to be negative,
Uh-huh.
so we can't go all the way around. Instead,
Oh, we have to go down.
we just make it negative. So this is negative pi over 6. Yep. I'm just giving people time to catch up their brains. You're going too quick.
For 1.
If we keep going, we can also do the inverse functions for secant, cosecant, and cotangent. I'll be honest, these are not as popular as the other ones, but we still can do them. No, not necessarily. But if we look at them, inverse cotangent, this is what it actually looks like. And then we have inverse secant, inverse cosecant. They're just not as popularly used, so I'm not all that worried about it. The domain of inverse cotangent is from negative infinity to infinity, and its range is from 0 to pi. The inverse secant, yes.
Can pi ever be on the bottom of a fraction?
Can pi ever be on the bottom of a fraction? Yes.
Like alone. So,
Like 1 over pi?
yeah.
That is a number, yeah.
What is this? Pi?
It's 1 over pi.
Just 1 over pi.
It's 1 over 3.14.
So could we necessarily, so we found the cosine of whatever, right? And we're looking for the, secant, right? Can we just flip it?
It's not that easy, unfortunately. The domain of inverse secant is from negative infinity to 1, union 1 to infinity, and its range is from 0 to pi. Oops. And inverse cosecant has a domain similar to inverse secant from negative infinity to negative 1, and then 1 to infinity, which makes sense since that's the range of secant and cosecant normally, so that becomes the domain of their inverse. The range has to be restricted between negative pi over 2 and pi over 2. Not really as concerned with the graphs themselves. I'm concerned with us being able to use them, similar to how we just did this with our unit circle. So to evaluate the inverse trig functions on a calculator / on your unit circle, because it does make it easy to do on our unit circle, secant inverse is evaluated as inverse cosine of 1 over x. So whatever number is inside the inverse secant function, you're going to use its reciprocal. Then you can do the inverse cosine. Same thing for cosecant and sine. Same thing for cosine and tangent. However, if the angle you're looking at is negative, you have to add 180 degrees or pi. Because 180 degrees is pi. So if you're in degrees, 180 degrees. If you're in radians, pi. So let's see if we can do this. We're going to first find what arctangent of 1 is equal to. Pi over 4. So Q is equal to pi over 4. If I was happening to ask you this in degrees, though, what would it be?
45.
Yep. 45 degrees. Okay, now we're going to take it a step further. What about inverse secant? So the way we're going to think about this is we're going to take this, and instead of saying inverse secant of 2, we're going to do inverse cosine of 1/2. How to get that number?
Putting it over 1.
Reciprocal, yeah. Putting it over 1 or just thinking flip the fraction. 2 is the fraction 2 over 1. So, yeah, so in that case, inverse cosine of 1/2 is pi over 3. What is that in degrees? 60 degrees. So cosecant inverse, which would be the same as sine inverse of the reciprocal. So I'm just going to flip that number over, and this one's going to take us a little bit of work to get to something we see on the unit circle. Because am I allowed to have square roots in the denominator?
No, you're not.
No. So what do I do? Rationalize, which means this becomes inverse sine of 3 square root of 3 over 2 times 3. Is anybody lost on what I just did?
I can't hear you over Taylor Swift.
Okay, calm down, Taylor Swift, right? Okay, so we take the square root 3.
Yeah.
It's kind of loud. What the heck?
So you just multiply the square root of 3 over 2.
We move it to the top, but it doesn't just disappear. We basically take it out of the square roots. We leave the 3 there.
So it's just 3 root 3
So
over
you
6.
3 pi over 6.
Take this, take
You
the square
switch
root 3,
You just switch.
move it up here, but leave the 3 behind. It's like a trailing behind.
Oh, okay.
We've done this before. It's just complicated when there are multiple things in that fraction. So then we have 3 square root of 3 over 2 times 3.
Can't you cancel out?
The 3's would cancel out, or the denominator is 6. Either way, you end up trying to answer inverse sine of square root 3 over 2. And what is the inverse sine of square root 3 over 2? Pi over 3, which is how many degrees? Which is 60 degrees. So each time we're doing this, we're referring back to our unit circle for these values. Or you're throwing it in a calculator. Although, I'll be honest with you, most of the ones we're going to ask you will be on the unit circle until we see an example like number 5. Number 5 says find y in radians if y is equal to inverse cosecant of negative 3. If we switch this, so if we switch this, cosecant goes with sine, so this is inverse sine of negative 1/3. Is 1/3 something you know from your unit circle? No, so we are going to need to switch to our calculator here. There is inverse buttons on your calculator, which is great, but it does ask for this to be in radians. So we press mode, we make sure we're in radians, and we press second sine for inverse sine, negative 1/3, and boom, what do you got?
Wait, say it again? After we get the answer.
Negative 1 over 3
Yeah, so inverse sine of negative 1 over 3,
I expected
is
the decimal.
negative.
the decimal.
Oh,
Is this what y'all got?
Yeah.
Great. I feel like Taylor Swift is still yelling at us.
She is.
I turned it down. Part B here says find the angle or find the Q in degrees if Q is equal to the arc cotangent of negative 0.3541. Yikes. First, we change it to arc tangent. And if I'm changing it to arc tangent, this becomes, don't work hard, 1 over negative 0.3541. No, you wouldn't leave a final answer looking like that, but we're in the middle of our work. No big deal.
Oh, wait. Calculator.
Yep. Bonus question though, how should you respond to this answer? Is it in radians or degrees?
Degrees.
So you have to do that before you type it in. You're switching your calculator back to degree mode.
And then next.
Or if you're using Desmos, you're making sure Desmos is in degree mode. And then you do inverse tangent of 1 divided by, what's up?
How many decimal points?
I like 4, but it depends on what the book is asking you to do.
negative 70.050.
I love that. We are wrong though.
What do you mean?
You need a fraction.
No, it won't be a fraction.
Why is it wrong?
It's a great question. Let's look back at the formulas we're supposed to be using.
Oh, 180.
Because the angle we're plugging in is negative, this second part of this piecewise function takes over. And so what do we have to add to our final answer? 180. So to make this make sense, here's what I'm going to do. I'm going to erase my little equal sign right here. I'm going to spread it out. And we're going to say equals 180 degrees plus the tangent of all of that, which you can just add 180 to the number on your calculator right now. And what do you get on that number on your calculator?
109.4991.
There we go. 109.4991 degrees. Evaluate without using a calculator. So calculator's away. Means we're probably going to use our unit circle, maybe some definitions that we know, all that good stuff. Okay,
Okay.
let's start off with what we know. It says to evaluate sine of tangent inverse of 3/2.
I'm lost.
Yeah, let's figure this out. So things that I know, because I don't recognize 3 and 2 as a part of a unit circle. So like my brain isn't thinking that we need to go there. My brain is going to start to think, okay, back to chapter 1. Let's figure out x, y, and r. Okay, inverse tangent is 3/2.
So if it's
Y over X.
So this is y over x. Very good. Tangent is always equal to y over x, so inverse tangent should have the y over x plugged in.
so that means square root of 2.
So this is what we did. We did this. Inverse tangent has the y over x plugged in, because tangent is usually equal to y over x. Inverse tangent, that's what's plugged in. Therefore, if I already know x and y, how do I find r?
That's very efficient.
Pythagorean theorem. Square root of x squared plus y squared. What do you end up getting?
4 plus 4 square root of 13.
And what is the square root of 4 plus 9?
Square root of 13.
And we can't reduce the number 13 to prime number, so we're going to leave it as square root 13. So now that we have this information, we got the x, y, and r from the inverse tangent of 3/2. Now it's just basically asking me for the sine of the angle at the same space.
It's a very big something.
Sine is defined to be what over what?
X over y. No, y over
Y over r. Well, look, here's y, here's r. I just have to rationalize my denominator. This becomes 3 square root 3, what? 3 square root 13 over 13. Inverse functions tell you, if they have numbers plugged in, they still tell you those definitions from chapter 1, x, y's, and r's. Once we have x, y's, and r's, we can answer the outside question because that's plugging in an angle. Our angle is determined by the x, y, and r from inverse tangent. Yes,
So that's the answer.
that's the answer.
Okay.
So is the tangent here just to like throw us off?
The tangent is there not to throw you off. The inverse tangent is there to give you this information. Because inverse tangent, the output of inverse tangent is an angle. And the input of a regular sine needs to be an angle.
Wait, so if the tangent of regular is y over x, why is it inverse tangent x over y?
That's reciprocal. Remember, that would be cotangent. Let's see this one more time. Let's see. In this one, again, inverse cosine is there on the inside. What is the definition of cosine?
X over r.
X over r. So inverse cosine would have x over r plugged into it. That's the normal output of cosine, which means it's the input of inverse cosine. So in this information, then we have x, y, and r. What is what?
We have r and x.
We have r and x. What is r?
13.
What is x?
Negative 5.
Negative 5. Thank you for making it negative. Remember, radius cannot be negative, so that negative belongs to the x. We need to find the y. I find the y using Pythagorean Pythagorean theorem, sorry. 13 squared minus negative 5 squared.
Can I use the calculator?
You can use the calculator to do this part. 13 squared is 169 minus 25 is 144. So square root of 144 is 12. That's another Pythagorean triple in case you remembered that one. 5, 12, 13. That's okay. You don't have to. You can do Pythagorean theorem every time, figure it out. So that means that the tangent of the angle that is used to make inverse cosine of negative 5 over 13 is y over x. Ta-da! The main gist here is that the input to inverse is the regular x, y's, and r's. The output to an inverse is an angle, which is what we normally plug in to regular sine, cosine, and tangent. You ready for a big kahuna?
No, miss.
Evaluate each expression without using a calculator.
Miss, I hate it.
Absolutely.
B should come before A?
Yeah.
Yes.
Okay.
Why? No, because why did you say it like that?
Ask and
I
you
know,
shall
bro.
receive.
Sorry.
Okay,
This looks hard.
so here's the things that I'm noticing. I noticed that there are two arc sines of 2 over 5 like plugged in here. So I could do this as tangent of arc sine. Ugh, I hate writing arc sine. I'm so sorry. I'm going to change that to sine inverse. They mean the same thing. Is that okay with everybody?
Yeah.
Yeah.
So it's like we're adding these two inverse signs together, right?
Adding?
Adding, because sine inverse plus sine inverse is 2 sine inverses if they're the same angle. Which is cool because, oh my gosh, we just did a whole unit on identities. And we have an identity for tangent when we have the sum of tangents.
Miss, I hate this.
That identity was the tangent of the first angle, which was sine inverse of 2 over 5. Same sign, tan inverse. Oh, nope, tangent of sine inverse,
We're just splitting it up in front of
2 over 5, divided by 1 minus
Oh, wait, okay. This is
the tangent of sine inverse times the tangent of sine inverse of 2 over 5. If you're like, Miss Quigley, where are you getting this formula from? This is from the sum and difference formulas from chapter 5.
So are we still gonna
Tangent of A, tangent of A plus tangent of B all over 1 minus tangent of A times tangent of B. That's what I'm doing here. What's up?
So are we still gonna need that formula sheet in this unit?
You can write those formulas on your document.
Or we can just use the formula.
For like during the class, are we still
Yeah.
gonna need that formula sheet?
Yep.
Is it gonna be heavily helpful?
How much do you have memorized?
None.
Oh, then yes.
0.
Yikes. Okay, so we need to evaluate this function because there's a whole lot of things happening. It looks like I made it more complicated, but it's about to simplify. Because remember, I gave you sine inverse of 2 over 5.
Yeah.
Sine inverse of 2 over 5 gives me information about x, y, and r. Sine is y over r. So 2 over 5 gives me y and r. How do I find x? Pythagorean theorem. This is 5 squared minus 2 squared. 5 squared is 25 minus 2 squared, which is 4. So 25 minus 4 is what? Square root 21?
Oh, what is this?
I don't know. I didn't make this playlist. So if we start to plug everything in, the tangent for this angle, tangent is y over x. And I'm going to leave it super undone correctly at first. So it's y over x plus y over x over 1 minus y over x times y over x. No, you would not leave a final answer with radicals in the denominator, but we're going to leave it for right now. And we'll just make sure we rationalize our denominator by the end. Let's clean this up a bit. You have 2 over square root 21 plus 2 square root over 21. So that's 4 over square root 21. And then you have 1 minus 2 times 2, which is 4, and square root 21 times square root 21, which is 21. Which one? The numerator? This is a common denominator, yes? I can add the numerators. 2 plus 2 is 4. And then top times top, bottom times bottom. 2 times 2 is 4. Square root 21 times square root 21, 21.
Could you explain the bottom part?
How square root of 21 times square root of 21 become 21? The square roots cancel out.
But wasn't it last unit it was like square root of 3 times square root of 2 was square root of 6?
Yeah, they weren't the same number.
Oh, so when I say number they cancel.
Yes. Yeah. Okay, to make this a little simpler, I'm going to change the number 1 into 21 over 21. Why would I do that?
I don't know.
So it had the same denominator.
Yeah, that's what I meant.
Leave the numerator. Subtract the denominator. 21 minus 4 is 17. Ah! Fractions and fractions.
Yeah.
Ah, the good old keep, change, flip. We keep. We change. I didn't even flip
Is the
it.
first one this long?
No.
We're gonna do it anyways.
Leave the long one out of the way.
4 times 21 is 84. 21 times 17 is 17 square root 21. And if that wasn't a radical in the bottom, we'd be done. But we're not allowed to leave radicals in the bottom. So we move, why not? It's just bad form. It's an irrational number in the denominator. So we move it to the top. What happens in the bottom?
17 times 21.
What is 17 times 21?
3, 5, 7.
So 84 square root 21 over 357. Y'all are going to hate me. What is 84 over 357
Oh my gosh.
in your calculator?
4 over 17.
Can you, yeah, it's 4 over 17. That fraction reduces to 4 over 17. And I didn't even give this much space last year.
You didn't?
I know.
So we're lucky. So you get more next year.
I made it work. So we do need to bring back those identities from last class.
I didn't think we needed all this.
Speaking of identities from last class,
Oh.
back to A.
Why can't we do the hard part things first and then the easy
That
things?
was the hard one. It's long.
No, I mean like before like this.
Well, because we couldn't do this if we didn't know how to do that.
Whatever.
Okay,
I agree after all.
cosine of arctangent square root 3 plus arcsine of 1/3. Here's the problem. You see how those numbers are not the same in the arctangent and arcsine?
Yes, we don't do it right.
We have two angles. So we're going to have the first angle. We need an X, a Y, and an R. Then we need the second angle. We need an X, a Y, and an R.
We do it twice.
We have to do it twice. Because those aren't the same number. If they were the same number, like they were in part B, we'd only have to do it once. If I tell you that arctan square root 3 is what's in there, did I give you X, Y, or R?
Y next.
Y and X. So here's Y, here's X. What's R?
Let's
Y and R. Oh,
what is it?
Ends up being 2.
2?
Square root of 3 squared is 3. Plus 1 is 4. Square root 4. For arcsine, what did I give you, X, Y, or R? Sine is always blank over blank.
X over
Y over R.
and then when
So then you do square root of 3 squared. What? Not square root of 3, I'm sorry. 3 squared minus 1 squared,
square root 8.
which is square root of 8, which reduces to 2 square root 2 if you make a tree and take out the pairs.
But we don't.
Ooh, okay.
It's not cheap.
I know, but you can do it. You can do hard things.
No, we can't.
I mean,
You can do it. I believe in you. So like
This,
cosine, we have a lot of options for how we do cosines of the sum angles, just because I know that your chapter 5 notes are somewhere. We have this formula for cosine of A plus B, which is what's happening here. We're adding two different angles together. That formula was cosine of A,
cosine, it's not this one.
cosine of A, cosine of B, opposite sign, sine of A, sine of B. But if we have that, cosine of A, we're going to treat this as angle A, and we're going to treat this as angle B. So question, What is the cosine for A?
Cosine for A?
Yeah.
Isn't that
Cosine is always x over r, so it's 1/2. What's the cosine for B?
1/3? No. Wait.
X over r.
2 root 2 over 2. No, 2 root 2 over 3.
Okay. Then I'm going to subtract the sine of A. Go back to the sine side, the A side. What is the sine of A? Mm-hmm. And then what is the sine of B? 1 over 3. Top times top, bottom times bottom. This becomes 2 square root 2 over 6 minus square root 3 over 6. Oh, that's nice. They're already a common denominator. I don't have to do hard work. This becomes 2 square root 2 minus square root 3 over 6. And that's it. That's it.
That. Why even start with this one?
So these identities aren't just done in chapter 5. There are times they come back in the rest of these chapters, especially this one for the thing we're going to do next class. But I'll tell you right now, we're going to skip this guy.
Yay!
Thank God.
You're welcome. It's a cool example, but I think your brain fried already.
What is OMIT?
Omit,
Omit?
skip.
There's not gonna be something like that on the.
I don't think so.
Thank God.
It's not hard. It's literally a plug and chug. Like you plug numbers in.
Miss, will
Like,
anything like those two examples be on the
Probably.
What would it
Yes.
any questions?
I don't remember.
She said probably.